Continuing on physical chemistry, chapter 15, we're in section 5 now. In the previous section, we derived the Maxwell distribution function. Now we're going to talk about how to apply the Maxwell distribution function. So we showed that the average speed is equal to the integral from 0 to infinity of the speed times this g function of the speed with respect to speed. Now, the average speed is equal to the integral from 0 to infinity of the speed of this whole quantity, mass, over 2 pi kt to the 3/2 power. Remember, k is Boltzmann's constant, T is absolute temperature, times e to the minus mv squared over 2 kt, m would be the mass of one atom or molecule, times 4 pi, the speed squared with respect to the speed. So the average speed is equal to mass over 2 pi kt to the 3/2 power times 4 pi times this integral from 0 to infinity of v cubed, the speed cubed, times e to the minus mv squared 2 kt dv. Now, to evaluate that, you have to use a table of integrals. In the table of integrals, we say that if we have an integral from 0 to infinity of x cubed times e to the minus ax squared dx, that's equal to 1 factorial over 2a squared, and that's just equal to 1 over 2a squared. Now, for that to be relevant to what we're doing then, a is equal to m over 2kt. So we have the average speed is equal to 4 pi times this quantity m over 2 pi kt to the 3/2 power times 1 over 2 over m over 2 kt squared. So we get the average speed is equal to 4 pi times mass to the 3/2 times 4 times the quantity k times t squared times kt to the 1/2 over 2 pi to the 3/2 times kt to the 3/2 times 2 over m squared. Simplifying out terms, whatever, we get k to the 1/2 times 4 over pi to the 1/2 times mass to the 1/2 times the square root of 2. Or put another way, we can write the average speed is equal to 4 times the square root of kt over 2 pi m, or we could distribute that 4 and get the square root of 16 kt over 2 pi m. 16 halves becomes 8, so we get the average speed is equal to 8 times k times t over pi times m. Now remember though, that's all if we're talking about one single molecule. That's why if we have k and a lowercase m. Now if we're talking about a bulk quantity, aggregate quantity of a lot of molecules, then of course we have the average speed is equal to the square root of 8 times the gas constants R times the absolute temperature divided by m times pi times the molar mass, and that would be in kilograms per mole. So now we have the average speed versus temperature here. Notice it's mass dependent. So lightweight molecules such as helium will be going fast compared to heavier molecules such as nitrogen. So we get the average speed squared is equal to the integral from 0 to infinity of the speed squared times this function, g function of v of dv, is equal to 3 kt over m, or 3 rt over m. Now remember, we said before RMS stands for root mean squared. So v RMS is the root mean squared speed. So the root mean squared speed is going to be equal to the square root of the average speed squared. Therefore, it's going to be the square root of 3 kt over m, or the square root of 3 rt over m. Now, VMP is going to be the most probable speed. And VMP is where, at the function, there's a peak there. Wherever that peak is, that's our most probable speed, because it's highest. The function is highest. The probability function is highest. And remember, when you have a peak like that, the derivative is equal to 0. So that's how we're going to find it. We're going to say the derivative with respect to speed of this function g of v is equal to 0. See if we can find MP. So substitute all that in. We have the derivative with respect to speed of m over 2 pi rt to the 3/2 times e to the minus m vmp squared. Remember, that's most probable speeds, over 2 rt times 4 pi mp squared is equal to 0. So we're going to pull out the constants. We get 4 pi times m over 2 pi RT to the 3/2 times the derivative with respect to speed of e to the minus m vmp squared over 2RT times vmp squared is equal to 0. Now, these constants, these can't equal to 0 unless, of course, you have a molar mass of 0, which doesn't make any sense. So we know this part's not equal to 0. So we're going to have to use the product rule to evaluate this derivative here. So we're going to have minus 2 mvmp over 2RT times e to the minus m vmp squared over 2RT times vmp squared plus 2 vmp times e to the minus vmp squared over 2RT is equal to 0. Now, we know that factoring this out, this term cannot be equal to 0. So that must mean the rest of it has to be equal to 0. So that means basically this term here has to be equal to 0. So we have the most probable speed times minus m times the most probable speed squared over RT plus 2 is equal to 0. Now, of course, there's the trivial case, in which case the most probable speed is 0. But then you're just at a temperature of absolute 0. So that's obviously not what we're looking for. That won't give us the function we need. So we're going to say the rest of this term is 0. So minus the molar mass times the most probable speed squared over RT plus 2 is equal to 0. So now we have m times the molar mass times the most probable speed squared over r times t is equal to 2. So solve for the most probable speed squared, and we get 2RT over m. So the most probable speed is just equal to the square root of 2 times the gas constant r times the absolute temperature divided by the molar mass, square root of all that. So this is a graph here of this function g, capital G, remember. So this is our function for speed versus velocity here. So you'll notice wherever the peak is at the top, the derivative is equal to 0. That's your most probable speed. A little bit higher than that, that's your average speed. And even higher than that, that's your root mean squared speed. Now let's say that arbitrarily that the most probable speed is equal to 1. Then the math works out to give you the average speed. It would be 1.128. And the root mean squared speed is going to be equal to 1.225. So instead of g as a function of velocity, we can also express g in terms of translational energy. Energy of translation. This is a epsilon subscript tr. Now remember, energy of translation is 1/2 mv squared. So v is equal to the square root of 2 times the energy of translation over m. So we have this differential form. dv is equal to 1/2 times 2 over m times 2 energy of translation divided by molar mass to the 1/2 power, minus 1/2 power, times the differential of the energy of translation, which becomes 1 over 2m to the 1/2 power times energy of translation to the minus 1/2 power, differential of energy of translation, just simplifying. So now we can substitute that back into g of v. So we get v, the speed squared, is equal to 2 times the energy of translation over m. That's just algebra. So we get the differential of the number of molecules at that speed divided by the total number of molecules, and that's equal to g of v dv. So now we have the differential of the number of molecules at speed v divided by the total number of molecules, and that's equal to m over 2 times pi times Boltzmann constant times absolute temperature, all that to the 3/2 power, times the natural number e to the minus mv squared over 2kt times 4 pi times the speed squared times the differential of the speed. So we get the differential of the number of molecules of that energy of translation divided by the total number of molecules is equal to 2 pi times 1 over pi kt to the 3/2 power times the energy of translation square root times the natural number e times the minus energy of translation divided by kt times the differential of the energy of translation. Now, the reason that version is good is because it doesn't have the molar mass or molecular weight or anything like that, which means the energy form of the formula is not material specific. So here's a graph of that function. We have 1 over n times the differential of the number of molecules at whatever energy of translation divided by the differential of the energy of translation. So here we are at temperature 300 Kelvin, and we'll have the exact same shape for any gas. Could be methane, which has, other forms of energy, such as vibrational and rotational energy. With a higher temperature, though, then the curve will get taller and wider. Now remember, energy of translation is proportional to kT. This symbol here, that means proportional to. And that is the end of section 5.